Okay, so here the question is question number 27. We have to choose the correct statements on oxygen among the following. First is ground state term for the oxygen atom is 3p1. B says the atom and the diatomic molecule are paramagnetic with 2 unpaired electrons. C says the most readily available singlet excited state for the oxygen atom has empty pi star orbital, and we have to choose among these 1, 2, 3, and 4, which is correct. Okay. So already I've given the solution over here. Now see, the term symbol is represented as 2s plus 1 Lj. Okay. Here the J is going to range from L minus S to L plus S for more than half filled. Okay, more than half filled, it will be J equal to L plus S. For less than half filled, it will be J equal to L minus S. Now, for oxygen in the ground state, this is the energy axis. Okay, here this is the 2s and this is the 2p. So we will be using the Hund's rule of maximum multiplicity and Pauli's principle to write the electronic configuration. The rule is that we have to ignore any closed shell while we are calculating the total spin multiplicity. Okay. When we calculate total spin multiplicity, which is nothing but ms equal to sigma ms. Okay. So this one is not used. Now we see that we have the up arrow spins as 3. So that is why we are having 3 into half, and down arrow spin as 1 over here. So that is why minus 1 into half, and that gives us the S as 1. Okay. So in the next slide, we will find out the total orbital multiplicity. Okay. So over here, we will see that for L, for the calculation of L, okay, we have to consider here there are 2 electrons in plus ml value, 1 electron in, and the ml value is 0, and there is 1 electron where the ml value is minus 1. Okay, so you keeping this in mind, now 2 into 1, 0 into 1, 1 into minus 1 will give you the L value to be as 1. Term symbol is this. Now ml value, if it is 0, then it is S, 1, then it is P, if it is 2, then it is D, if it is 3, then it is F. So using this, we can say now that it is going to be 3p2 and not 3p1. So the first option obviously is wrong. So in any option where we have A, we have to ignore. So over here, option 1 is having A, option 3 is having A. So these 3 options, 2 options are rather not correct. We have to choose from B or from option 4 and option 2. We have to choose the answer. Let's see. Now, I have here drawn the triple state MO diagram. Now, why I'm calling this as a triple state, we will learn shortly. So this is the, you draw the MO diagram using the atomic orbitals. Okay, so this is the atomic orbital of oxygen, 1s, 2s, and then 2p. You draw 1s, 2s, and then 2p. All right. We use both these atomic orbitals. We know according to the rule of linear combination of orbitals, we will say for MO theory, 2 atomic orbitals combine to form 2 molecular orbitals. So obviously, this is the bonding orbital and this is your anti-bonding orbital. Okay. Similarly, for 2s, we have the bonding and we have the anti-bonding part. For p orbitals, there can be 2 types of combinations. That is, we will say head-on combinations or side-on combinations. So the head-on combinations will be producing the sigma molecular orbital and sigma anti-bonding orbitals, whereas the side-on will be producing the pi bonding and pi anti-bonding. We just need to arrange now 16 electrons, again following above principle and Hund's rule of maximum multiplicity. So what we will do, the lower energies get filled up first, then followed by the higher energy, and so on. And we find out eventually that in the pi star orbitals, there are 2 unpaired electrons. Okay. So since there are 2 unpaired electrons, so if we use the formula for spin multiplicity calculation, 2s plus 1, we will say now that will be coming out to be as, because s is going to come out to be half plus half is going to be 1. So 2s plus 1, if you just plug in the value for s, you get as 3. So this is the MO diagram for your triplet oxygen. However, use the same molecular orbital diagram for the singlet oxygen. Just think this unpaired electron now pairs up after getting some amount of energy. This unpaired electron now pairs up. So over here, there are no unpaired electrons. So S now here will be plus half with added to minus half. So S becomes 0. So if you use the formula 2S plus 1, then obviously the multiplicity, spin multiplicity will be coming out to be as 1. That means this is the MO diagram for a singlet molecular oxygen. All right. And we can see over here that this particular pi star orbital is empty. Okay. So over here, we will say that option C is correct. And also option 2 is correct because both in the molecular oxygen and also, as we have seen before, for atomic oxygen, there are 2 unpaired electrons. So obviously our answer will be both B and C, the options are correct. Let's go for the next question. All right. Again, a very simple question. Okay. The correct statement for the peroxydisulfuric and dithionic acid from the following is each of these have 2 OH bonds. Peroxydisulfuric acid has 1 OH bond, dithionic acid has 2 OH bond, peroxydisulfuric acid has 2 OH bond, and dithionic acid has 1 OH bond. Each of these have only 1 OH bond. Simple way to solve is draw the structure. And that is the structure. Okay. This is your peroxy bond. Also, this acid is known as Marshall's acid. So it is basically H2S2O8, okay, oxidizing agent. And as you can see, this is having 2 OH bonds. For the dithionic acid, there has to be an SS bond. That is how you remember this thing. Okay, and we can see there are again 2 OH bonds. Obviously, our option 1 is correct over here. Next question. Here it is given the correct statement for a CON2 ligand in the complexes trans IRCl CO PPH3 whole twice and trans IRCl N2 PPH3 whole twice. N2 is a better sigma donor. Option 1 is N2 is a better sigma donor and better pi acceptor ligand than CO. CO is a better pi donor and a poorer pi acceptor, sigma acceptor ligand than N2. CO is a better sigma donor and a poor pi acceptor ligand than N2. CO is a better sigma donor and a better pi acceptor ligand than N2. Obviously, over here, option 4 is correct. Why it is correct? The reason for that is that if we consider CO, what we will see is that the electrons, they actually lie over CO. The electrons, they lie over CO. Even if you're doing the MO diagram, you will find that the electrons are lying towards CO. Okay, and there is electronegativity difference. Okay. However, in case of the nitrogen, okay, in case of the nitrogen, there is no electronegativity difference. So this is the first prime factor. Now, what it means that the donation, because the MO diagram will be telling us that the oxygen pair, the lone pair is lying over the carbon. So bonding will take place from the carbon. Okay, bonding will take place from the carbon, And when it has to accept the electrons from the metal, the antibonding orbitals of the CO, okay, they are better placed to accept the electron pair from the, or electron density from the metal. And that's why we will say that CO is a better sigma donor and a better pi acceptor than the nitrogen. And just to the take home message over here is going to be that there is electronegativity difference between CO, whereas for nitrogen there is no electronegativity difference. Next question. Here we have been given among the following divalent metal ions, which forms polymeric compound when the ligand used is C5H5 minus, also basically called as cyclopentadienyl ion. Options are given as vanadium, nickel, Mn, Co. Again, it is a memory-based question. All right. Over here, you have to remember that it is magnesium, not magnesium, manganese that is going to form a polymeric compound. So in the solution part, this is the unit that you can see now is having the polymeric unit. Okay. Whereas for vanadium, it is a 13 electron system. It is highly air sensitive and it is a paramagnetic compound. For nickel 2, we will find that it is a 20 electron system. Okay. And in presence of oxygen, it goes and loses 1 electron to form a 90 electron system. In case of cobalt, it easily forms a cobalt-to-selenium ion, okay, because it goes to the stable 18 electron configuration. Okay, so it easily forms the COH5, C5H5. There should be a twice over here. I have missed that. Okay, so I'm going to include that. There should be a twice here. All right. So our answer will be now Mn. All right. Here again, it is a memory-based question. We have to match the list 1 with 2, metalloprotein and what kind of metal it contains. Okay. Carboxypeptidase is basically going to contain zinc. All right. Oxygen evolution complex, which is present in the PS2 of plants, that is photosystem 2 of plants, will be having a cluster of Mn. Okay, that is Mn4O4Ca. Hemerythrin is going to contain iron. All right, and the coenzyme F430 is going to have nickel. All right, so that way we will say our answer is going to be